In the third part of the lesson, we'll cover creating 3D constraints between assembly components and generating 2D views from the 3D model. Why do we need constraints when we can move the part to the desired position using 3D manipulation and fix it? For small assemblies, this is quite possible. But what if the assembly has several hundred parts? For creating large assemblies with many assembly units, 3D constraint will be an indispensable tool for their creation. All 3D constraints are found on the command panel in the 3D constraint group. We'll start with the Symmetry 3D constraint. Select the command and specify the model elements that you want to align symmetrically, such as the faces of your objects. Then specify the symmetry plane. It could be a standard plane or a custom work plane created by the user. We'll use the ZX plane as the symmetry plane, after which the selected elements are arranged symmetrically relative to the specified plane. If we change the position of one object, the other will automatically adjust as well. All created constraints are also shown in the 3D build history. As we can see, both bodies have an entry showing that the symmetry constraint is applied, and it indicates the elements between which this constraint was created. In this case, the faces of our objects. We will remove this constraint so that it won't get in the way when demonstrating other types of constraints. The next constraint is Tangent 3D. Select the command. Indicate the cylindrical face of the plug and the face or edge of our bracket. The result is a tangential constraint between the selected elements. If we enable the bottom view, we'll see that the cylindrical face of our plug is now tangent to the side plane of the bracket. Now our body can only move while remaining tangent to the plane we specified. Let's cancel the created constraint using Ctrl-Z. Above that is the Angle 3D constraint. With it, we can specify the angle of inclination between the selected faces of the 3D models. Let's fix the bracket. Activate the command. Select the elements between which the angular constraint should be created, such as planes. Then, if necessary, we can specify the axis of rotation in the command line and enter the angle at which we want these planes to be rotated relative to each other. For example, 30 degrees. Let's go back to choosing the axis. Cancel the command and repeat the application of the angular constraint. If we choose a different axis of rotation and enter 45 degrees, you'll see that the inclination of the parts changes according to the selected axis of rotation. Cancel the command, unfix the bracket, and use the next Mate 3D constraint. With its help, we can, for instance, ensure the concentricity of cylindrical elements. Select one hole, then select another hole, and achieve concentricity between the holes. If we look from above, the holes are concentric. With the Mate command, we can also set the mate or distance between the selected planes. For instance, choose the top plane of the plug and the bottom plane of the bracket. In the command line, the distance between these elements is displayed, and we can enter a new distance, like 0. Now these elements align along these planes, and considering the previous concentric constraint on the holes, these elements are now fixed by the lower plane, but they can still rotate relative to each other. For example, let's use the 3D rotation command. Since they are only fixed with a concentric constraint, they still have 1 degree of rotational freedom relative to each other. However, for mating holes in different models, it's more convenient to use the Insert 3D constraint. With it, we can simultaneously fix the hole mate and the plane of their placement relative to each other. Remove the previously created mate constraints. Slightly separate the parts and apply the Insert 3D constraint. As the first constraint element, select the upper edge of the hole on the plug. As the second constraint element, select the lower edge of the hole in the bracket. As we can see, these holes have aligned, thus forming their concentric contour and aligning along the plane. Finish the command by pressing Enter. As we can see, the insert constraint has been added. After creation, the insert and make commands can also be edited directly in the 3D history. For instance, the current distance between our holes is 0. If we set 10, then the distance between them changes to 10. Let's undo the changes. To finally fix our parts relative to each other, we'll add another Insert 3D constraint. Select the bottom edge of the bracket hole and the top edge of the plug hole. Click Enter. Our part has shifted slightly because it wasn't fixed. But we can easily rotate it by using the movement commands or by setting another constraint, such as 3D alignment of the bracket's side edge and the standard YZ plane. Now our part is aligned. Return to isometry and add new components to our assembly. Choose the bolt. Add it to the graphical space and apply the Insert 3D constraint. Select the edge of the bolt head on one side and the upper edge of the bracket hole on the other. As we can see, this screw fits perfectly. If we want to change the direction, we can use the aligned option in the command line to change the insertion direction. Press Enter to complete the command and add new components to our assembly. For instance, a washer and another component, a nut. Add the necessary constraints to the washer and nut. Click Enter and also apply an Insert 3D constraint to the nut. As we can see, we have a complete bolted connection. Already inserted components can be freely copied. For instance, copy the bolt, and by repeating the operations of copying, inserting, and applying 3D constraints mentioned earlier, we'll end up with a finished assembly unit. So, I hope creating constraints is now clearer. Now let's talk about generating 2D projections. For this, we use the commands from the 2D Views group. To create standard views, we'll apply the Projected View command. Click on the command. In the command line, we're prompted to select the objects that will participate in the 2D view creation. Select the entire assembly. Press Enter, then choose which sheet you want the projections to be inserted onto. Let's select A3. Add the views to the sheet space. When the views are inserted, we can generate additional projections without reselecting the assembly or choosing a sheet again. This is done using the 2D projection command. Click on the command, select the view from which to create a 2D projection, and insert it into the sheet space. Just below is the 2D section command, which we can use to create a section view. Click on the command, choose the view on which to specify the section plane, and define the section plane's location. That's all. The section command works similarly. Go back to Model Space. Click on the section command. In the command line, We can choose which element we want to use as the cut plane. This could be a face of the body or 3 points through which the new plane will pass. Select a face. Specify a point and the space where the resulting section will be inserted. For example, A4. From the inserted cut plane section, you can also create additional 2D projections using the 2D projection command. On views created this way, you can add dimensions, surface roughness, positions, and other necessary information related to drawing design. This 5th lesson, focusing on working with assemblies and arrays, is coming to an end. Along with it, the entire course on the basics of 3D modeling on the nanoCAD platform wraps up. I hope you found this course interesting and useful. Thank you for your attention, and see you next time.